All right, so first off, before we get into trig integration, like the way we're going to be working it, like it's not just trig integration where we're integrating sine and cosine and stuff like that. These are problems that have multiple trig functions in them, and there are tricks as to how to do them. Okay, so things that you need to remember. So I'll put that right here. So you want to remember the following. And I know you guys all still remember all of your trig identities, right? So things you guys need to know. Sine squared x plus cosine squared x is equal to 1. All right, that's 1 down. Okay. And then power reduction. So sine squared x is equal to 1 minus cosine of 2x over 2. That one, did anybody remember that one? Power reduction, okay? Very important one. And cosine squared x has one just like it, just that there's a plus in it. So this allows you to get rid of the square term for sine or cosine and rewrite it so it doesn't have an actual square term. Okay, it happens to have a double angle. So just just for you guys to see them right there, okay? These are important because these are the ones that we're going to use to try to break things down. Now remember, we can manipulate sine squared x plus cosine squared x equal to 1 to read sine squared x equals 1 minus cosine squared x, right? Or cosine squared x equals 1 minus sine squared x. We can do whatever we want with these things because these are identities. So just know that, right? We can always mess with stuff just to make it fit whatever we want. But these are the three main things you're going to do. Okay, now I'm going to break this into two different lessons, and I probably should have put that up there. This is actually section 8.3 part A, because for the first half, we talk about sine and cosine problems, then we talk about secant tangent problems. So today we're only going to do sine and cosine problems. Okay, so let me give you an example of what I'm expecting you guys to be able to do. By the way, that is the whole lesson right there I just finished. Okay, the rest is pure problems that you're going to try to do. Okay, I will give you some hints within those problems. Okay, so we're going to do the integral of sine cubed x cosine to the fourth x dx. So notice, when we call this trigonometric integrals, we don't just literally mean, like I said, the integral of, sine or cosine or secant squared. Like, no, we're talking about like, okay, here's a mixture of trig functions. How do you do these? Okay, so one thing that I can give you a hint is, let me write this right here. An odd power can be broken down. Actually, should be. But sometimes you don't have to, but most of the time you want to break it down. So, this problem right here, I want to break down the sine cubed of x. Okay? All I'm going to do is take 1 away from it. Okay, so I'm going to rewrite it like this. Sine squared x cosine to the fourth x sine of x dx. Now notice, I put the sine of x dx at the very end, but sine of x times sine squared of x is sine cubed of x, right? So it is there. I just kind of separated it a little bit. Okay? Now, what I'm going to want to do at this point is there is going to be u substitution. Okay? This part right here is what you want your du to become. Okay, that's what your du has to be. So what does my u have to be if my du has to be sine x dx? Cosine, right? I need cosine to show up. So what I'm going to do, I'm going to rewrite sine squared x as 1 minus cosine squared x, cosine to the fourth x, sine of x, dx. And I'm going to start off with my let statement, let u equal to cosine of x. That means that du is negative sine of x dx, or you could say negative du is sine of x dx. So notice here's that part that we were mentioning. Okay, so let's start to substitute here. So this problem now looks like this: the integral of 1 minus u squared u to the fourth du, and actually I messed up. I should have a negative in the very front. Sorry about that. So that looks a lot easier. Let's distribute, right? Distribute, and from there integrate. So it should be easy until the very end. We got to plug stuff back in, right? So this is going to be negative. I'm sorry. I was going to integrate it immediately. This is going to be u to the fourth minus u to the sixth du, and now I'll integrate. So this is negative u to the fifth over 5 minus u to the seventh over 7 plus c. And let's plug in the u value, which is cosine of x. So negative cosine of x to the fifth x over 5 minus cosine to the seventh x over 7 plus c. And that would be your answer for this problem. Good, you saw that I was trying to trick you. No, thank you for that. Yeah, it should be a plus. You're supposed to distribute that negative. I distributed it the first time. I get half credit. No, I get actually a 66% because I did get that plus C right too. Yeah, so that should be a plus in the middle. So there you go. Are these problems insanely difficult? They look really bad sometimes. Okay, but they're not too terrible. You just got to make the right substitution, okay? And like I said, the trick is to look for those odd powers. Okay, if you see an odd power, you break it down by 1, and that's going to become your du. Whatever you get, like sine of x dx, cosine of x dx, that's going to become your du. Okay? Once you figure that out, then okay, well, if my du is this, what's my u have to be? And then you change everything as much as you can to have that u term. So that's why I did like this right here. The changing of sine squared x into 1 minus cosine squared x, right? Because I'm trying to get that u term to show up as much as possible. I only want 1 of the sine x dx because it's going to be substituted eventually, right? But once you do that, I mean, this part right here, integrating this was pretty easy, right? It's just power rule. Go ahead. Oh, remember we talked about this yesterday. We don't know whether the c is positive or negative. So even if c, I could put minus c, but then if c is negative, then it's really plus c, right? So, but since we don't know, it doesn't matter, right? We could say I did distribute it into the c, you just don't see it, right? Right? We can put it like that. But yeah, since we have no idea, I think I said the only way we can actually see an impact on it is if I had an initial condition that would give me the opportunity to solve for c, and then once I know what c actually was, then it could affect it in a negative way or positive way. So, yeah, you could always just leave it plus c. If you put minus c, I don't think it's wrong either. But I think it's just common to see it as a positive. All right, let's try another one. I think we have 3 examples to do. So here's example number 2. So we're going to have the integral of sine squared x cosine to the 5th x dx. So which one do I break down? Cosine, right? So let's rewrite it. Integral of sine squared x cosine to the 4th x cosine of x dx. Remember, cosine of x dx is going to be my du. So what's my u? Sine, right? So I need everything to become sines. can I change that to 1 minus sine to the 4th x? No. Good. Cannot do that. Right? I can do it only if it's a power of 2. But there is a theorem that says it does not work for any power other than 2. Okay? Uh-huh.
You want to be able to do like 1 minus sine squared and squared?
Yes, you can do that. So good. So let me show you exactly what he was talking about. So check this out. So I can rewrite this as cosine squared, right? Here's what I like about math is that even though it doesn't seem you should do it, but you can do it, right? You do math the way you know how to do math. So we're just going to kind of create a little shortcut here. I can do that. And then I can rewrite it as 1 minus sine squared of x squared, right? The quantity, like you said. So this will be the integral of sine squared x, 1 minus sine squared x squared cosine x dx. Now at this point, this is where I'm going to do my u substitution. I mean, you could expand it out if you want to. That's completely up to you. But I'm going to do my u substitution at this point. So let's let u equal to sine of x. So du is cosine of x dx, right? And here's that du portion I said, right? Like notice how that's what's going to be removed when we do our u substitution. So here we go. Integral of u squared 1 minus u squared squared du. See, I'd much rather expand at this point because it looks simpler than have to worry about doing it with the sine squared x there. So let's go ahead and do that. Let's expand here. U squared. This will be 1 minus 2u squared plus u to the 4th du. So if I keep going, give me a second. Sorry about that, but hopefully you beat me to it, and you're already done integrating, right? So u squared minus 2u to the 4th plus u to the 6th du. By the way, you notice how I put parentheses? How many of you guys write it like this without the parentheses? I think a lot of people do that. Okay? That always bugs me because are you forgetting to put a du here? And then this is a normal term? And then did you forget to put an integral there and you just put d, right? Like it's open to interpretation, right? So I always tell people keep whatever's being integrated in a parenthesis so that the reader knows this is what's going to be part of my integration. Is it wrong to do it the other way? No, I just think it looks cleaner, right? You don't want to leave anything open to interpretation, so make sure that you make it obvious. So anyway, we have u to the 3rd over 3 minus 2u to the 5th over 5 plus u to the 7th over 7 plus c. And since u was sine of x, just plug it back in, and you're done. So sine cubed x over 3 minus 2 sine to the 5th x over 5 plus sine to the 7th x over 7 plus c. So you see what I mean by this is not just like normal trig integration. Like this is like weird trig integration. Okay, if you get too many trig functions in one place, what do you do? Right? Because we can do the other stuff. I mean, that's just definitions. But here's like, okay, utilize it. What do you know about it? So, yeah, they're not, like I said, they're not tricky. They have specific ways to do things, right? You see odd powers, break one down, right? If you see only even powers, well, we'll talk about that right now. What happens if there's only an even power? Are we good with this one? Any questions? All right, so here we go. Now, I just want to make sure you guys understand that they can put upper and lower bounds on these problems, right? Like they could have said, okay, now that you integrated, you were going from 0 to pi over 2, go ahead and plug it in, right? Like you can do that. I usually don't do too many of those problems because I have faith that you guys know how to use the fundamental theorem of calculus, okay? So a lot of times I don't want to waste extra time just trying to find an actual value. Okay, I'm more interested in doing the process. The value should be simple for you to figure out. Okay, especially with calculators being available and stuff like that. So make sure that you always know your trig values, right? Know your sines of 30s, 45s, 60s, 90s, your 120s, 225s, etc. Right? Be able to calculate those things in your head. And if you don't have them memorized, how many of you guys have them memorized? Like if I were to say like 0, 30, 45, 60, 90, and every other interval in between. So like 120, 150, 135, 180, all of those for all your trig functions. Anybody here have them like memorized like instantly? Do you guys do like that whole finger thing? Okay. So, that'll work. We'll talk later about a different way to kind of do it based on memorization of just the first 90. And then from there, it's all just, angles that are like them, right, in different quadrants. So our reference angles. You guys learned reference angles, right? Yeah. Okay, that was just a while ago. So, all right, here we go. Last one. We're integrating cosine to the fourth x dx. Now notice we don't have two different trig functions, and this is not odd, right? So what you do in this case is you're going to break it up into two evens, okay? So let's do that first. The reason why we break it down into two evens is, actually, let me show you why. If I were to do this, okay, don't write this down what I'm about to do. Do I know an identity for a cubic? No, so that means I got to break it down again, right? So, and at this point, I know identities for that, okay? But instead of trying to break them down into a power of 1, a cosine of x with the power of 1, because notice none of these are odd, we're going to use our power reduction formulas, okay? So, remember that we wrote them down. Cosine squared x is equal to 1 plus cosine of 2x over 2. So that's what we're going to do. 1 plus cosine of 2x over 2. 1 plus cosine of 2x over 2 dx. And we'll factor out that half. So half and half is a quarter. You know, in my lame math jokes, my wife uses half and half for like baking and for drinks and stuff like that, like coffee and all that. And I'm like, why don't they just call it a quarter? And she didn't get the joke. And I'm like, half and half, half. And she didn't get it. So it's one of those things where you're like, okay, I don't regret saying it, but I do, because I thought it was hilarious, but she didn't. Anyway, so here we go. We have this. Now, at this point, what I'm going to do is I am going to expand this, okay? I am going to expand this thing. So, let's see, I have 1/4 integral of 1 plus 2 cosine of 2x plus cosine squared of 2x dx. All right? Now, I can integrate this, okay? That's easy to do. I can integrate this, right? I can integrate that using a u substitution, let u equal to 2x, right? du would be 1/2. So I can do that. What I can't do is that. Because what am I going to let u be in order to get cosine squared 2x to kind of work out? If I let u equal to 2x, then I still am stuck with the cosine squared. Okay? So what I'm going to do, yet again, is I am going to use the power reduction formula for that. Okay? Now let me show you what the power reduction formula is going to look like. So you see this part right here, in the green part, how this becomes that when you power reduce? Okay, x becomes 2x. Well, what if I change it to a 2x? It becomes a 4x. Good. Because it's double that angle, right? So I'm going to go ahead and put that in. So a little bit of manipulating the information that's given. Now, from here on out, it's just a lot of algebra until we actually integrate, okay? You see that power of, not power of 2, the denominator of 2 on that one fraction? I am going to factor it out, okay? But you might say, well, this doesn't have a denominator of 2, and neither does this. Well, whenever you factor out a denominator of 2, the terms that don't have one, you multiply them by 2, okay, or by whatever your denominator is. So, when I factor out that half, this becomes a 1/8. Okay? So 1 times 2, that's 2, plus 4 cosine 2x, plus, now since that other fraction lost its denominator, I'm just going to write 1 plus cosine 4x dx. See, here you thought this problem was going to be easier because it was smaller, right? This one's worse. All right, let's combine things that we can, then we'll start to integrate. Okay, so 1/8 integral of 3 plus 4 cosine of 2x plus cosine of 4x. And notice now I can actually integrate everything, because cosine of 4x, I'll just let that be some kind of u substitution, or it's going to have to be a different letter, a w substitution. But here we go. Are we okay so far? I mean, kind of weird, but using a lot of identities, right? Breaking stuff down by the use of identities and allowing us to get it to a point where we can integrate something. So here we go. We got 1/8. This will be 3x plus, now let's do a quick u substitution here. So let's let u equal to 2x. So du will be 2 dx, so that's 1/2 du. That's dx. Okay, so I'm going to just kind of write it out in a different color here for us, okay? 1/2, let me put some room in here. Actually, you know what? Since it's a half and I have a 4, I'm just going to put a 2. So it's 2 integral cosine of u du. And then let w equal to 4x. So dw will be 4 dx. So 1/4 dw is dx. Again, that is the proper way to do multiple substitutions using different letters. Again, if you just want to use u, it's okay, but on an AP exam, you might want to change it up. That way they're not becoming sticklers and stuff over it. So this is 1/4 integral cosine of w dw. Are we okay? So everything's just kind of been placed in there so that we can integrate it easily. So here we go. Final steps. 1/8. 3x plus integral of cosine of u is sine of u, so 2 sine of u plus 1/4 sine of w plus c. Since u is 2x and w is 4x, then what I end up with is 1/8 3x plus 2 sine of 2x plus 1/4 sine of 4x plus c, and then we distribute that 1/8 to finish this off. So 3/8 x plus 1/4 sine of 2x plus 1/32 sine of 4x plus c, and it's as easy as that. No, I'm just kidding. Yeah, it's a bit of a hassle, right? It is a struggle to get through it. But this is what you have to be able to do for today. Okay? Tomorrow we will continue with different functions. But today is just sines and cosines.